So we now know that buffers are made up of weak acids and weak bases. We said we stay away from the strong ones because the strong ones are too powerful. They will reach out, they will grab the proton, or they will give up the protons that are needed, and they will never really want to give them back or take them back in again. And a lot of times that's not what we want to happen. We want a temporary home. We want a temporary kick them to the curve, but bring them back if you need them a little bit later on. So weak acid and weak base are very important. However, something that we didn't talk about in the last video is that they want to be complementary. And when I say that, I want to say they want to match. Okay, so when I pick out a weak acid and a weak base, because it requires both, when I pick out a weak acid and a weak base to make the buffer with, I want to make sure that they're complementing each other, meaning that I want to limit the variables that take place in the buffer system. So what does that mean? What am I basically trying to say? Well, here we go. Let's say that I'm making a buffer and I'm reading directions. And the buffer says, you want to use citric acid in order to make the buffer with. All right, well, that's good. That is the weak acid part to make the buffer. So what is the weak base that needs to make the buffer? Because we need both. Well, that's the complementary version, meaning that I need to choose a weak base that has something in common. Well, if this is citric acid, then I need something with citrate. I need that ion species involved in the base. And most of the time, the cheapest ones here are going to be sodium or potassium. And you're going to find me write down sodium a lot of times because those are the easiest ones. They dissolve in water. There's no issues with them. They're cheap, easy to obtain. Sodium and potassium are great. So citric acid and its complement would be sodium citrate. They both have the citrate ion in common, and this is my weak acid and my weak base combo. That's typically how I would make a buffer almost every single time. All right? Okay, well, let's take a look at acetic acid. Acetic acid is weak, so what kind of base would I want to use for that? Well, I would want the acetate form, CH3COOH. The CH3COO is what's left over once it gives off a proton, so I would want the acetate version of that, and this could be sodium acetate in order to make it. So whatever ion this acid has, or the ion that the base has, you want to make sure that the other one, the other acid or the other base, will have the same exact ion on the inside. Now, this is not a requirement. It's just recommended. Because if I do this as a combination, the acetic acid and the sodium acetate, or the citric acid and the sodium citrate, what I'm doing is that I'm making sure that everything is as simple as it can be. I'm not including tons of different ions in the solution for a buffer that could maybe react and do other things with the reagents. I don't want that to happen. So if I can make sure that it's as simple as possible, then I can kind of control all of these side reactions or byproducts that begin to form when I incorporate a buffer into my processes. Okay? So that's kind of the way that we would formulate a buffer. Pick out a weak acid, pick out a weak base, but preferably make sure that they have something in common, and that's typically the ion. In this case, acetic acid and sodium acetate, citric acid, sodium citrate. You would kind of want those to match. Now, if you're lucky to make a buffer, you would follow a recipe, right? And the recipe could say you want to make 100 milliliters of a buffer, and the buffer has to be 4.8 millimolar acetic acid and 5.8 millimolar sodium acetate. How would you make it? These are the easiest problems to do with buffers. And the reason is because it goes back to basic solution prep, right? I mean, I know this is millimolar here, and I did that just to give you a unit that you're not comfortable seeing all the time. But I know we've got to convert that out of millimolar and get it into molar, because that's what you're comfortable using maybe. But it gives me volume, it tells me the concentration of the weak acid, it tells me the concentration of the weak base. I just need to figure out how much to weigh out and mix together to make the buffer with. So we're going to go through and we're going to work out this problem. But I want you to understand that this is the most basic type of buffer problem. It is a recipe. It's just like working with molarity in this case because it's in millimolar. I've got a volume that I'm wanting to make. I'm just following a recipe. I just need to know how much of the ingredient to weigh out. That's it. So to solve this type of problem, I've listed the formula weights of each one of these molecules over here to the right-hand side. I see the formula weight for sodium acetate, 82.03, and that of acetic acid down below, formula weight of 60.05. So I need to figure out how to make 100 mils of this buffer. There's my weak acid, there's my weak base. So these types of questions could maybe say A, which is the weak acid, B, which is the weak base, C, how much do you weigh out of each to make this buffer? So acetic acid, of course, is the weak acid, and the sodium acetate, of course, is the weak base. How do I know that? Because this says acid, and that's my weak acid. All right, those questions couldn't get any simpler. So I'm going to skip down to C. How much should I weigh out of each one of these, right? So I'm first going to start with 4.8 millimolar solution of acetic acid. I got to figure out how much do I weigh out in order to make this amount of buffer. All right, well, the molarity equation is moles divided by liter. Here we have 100 mil buffer. That's how much I need to make. So 100 mils is 0.1 for liter. M is going to stay for mole because that's eventually how I will get to weight, but I need the amount first. And the concentration is in molarity. Well, the problem here is that the problem gives me millimolar and not molar. So milli means 1,000, and I move the decimal 3 times. So this is actually 0.0048. So move the decimal 3 times, 1, 2, 3, that gives me 4.8. So 4.8 divided by 1,000, 0.0048. All right, so I'm going to bring up the calculator so that way you can watch me go through the calculation part. So 0.0048, and I'm going to multiply by 0.1. And that gives me 0.00048. But that's in mole. Of acetic acid. Well, to get to grams of acetic acid, I need to multiply by the formula weight. And that formula weight is 60.05 grams per mole. All right. So again, just like all the other calculations that came before, we've talked about these calculations in the very first module, and now we're ending up with similar calculations in the last module. So 0.0288 is going to be the answer. And this is going to be in gram. Now, acetic acid is a liquid, so probably what I would want to do is I could use density to calculate milliliter, but it's probably going to be just as easy to take the volumetric flask, 100 ml volumetric flask, and add acetic acid dropwise to the flask that is located on a balance, and just allow me to kind of figure out how much am I adding according to the weight, and then I can kind of stop when I get close to 0.0288. I'll just write down exactly how much that I've used. But I could use density if I really wanted to. I could use the density value in order to get to milliliters of the liquid that is needed. So this part is now check. I've calculated how much acetic acid that I need to use to make that buffer according to acetic acid. So that amount goes into the volumetric flask. But I need to add a second component, and that second component is 5.8 millimolar sodium acetate. I do it the same way. So 0.0058 molar is equal to moles divided by 0.100. I'll multiply each side of the equation by 0.1, so that ends up being 0.00058 moles of sodium acetate. And then I'm going to multiply that number by the formula weight, which is 82.03. All right, so I'm going to move my calculator over. 0.00058 times 82.03 is 0.0475 or 0476. And that's in gram. So I'm going to take that same flask that already has my acetic acid in it, and I'm going to weigh out 0.0476 grams of sodium acetate, and I'm going to add it to that same flask. Component number 1, component number 2, filled to the line with DI water, invert and mix, and now this is my buffer solution. This buffer has a weak acid component. This buffer also has a weak base component, and now both of those are swimming together in unison in that flask, ready to negate any positive or negative charge that might come its way. All right, so again, these are the simplest types of calculations that you're going to see. It will give you a concentration unit. It will tell you how much to make. It will tell you what you're using. And we can go on in this calculation and do something else, but I'm going to save off to that to another video. But we're just looking at recipes now. That's all that we're doing for this part of the lecture module. We're looking at recipes. How much do I use? How much do I weigh out? How do I mix it? And this is the proper way to make the buffer. So in the next video, we'll continue on and we'll do some other examples that will not be like this one. They'll be a little bit more advanced with maybe some spins on different perspectives of a buffer problem.